Hello, this is a supplemental video that describes the notion of cardinality. In simple terms, cardinality is the number of elements in a set. This can easily be established by just counting the number of elements in a set if the set is finite. However, it is impossible to count an infinite set, such as natural numbers. In this video, we will discuss the cardinality of both finite and infinite sets. In discussing infinite sets, we will focus on countable sets such as positive integers. We will learn how to reason about the cardinality of sets using counting or defining one-to-one functions from the set to a known cardinality of a set. So let's take a look at the cardinality of finite sets. If A is finite, then the cardinality of A is the number of elements in A. The notation is cardinality of A is these vertical bars A. If it's finite, we can easily establish this by counting. However, if the set is large, the counting is always not very fun to do. For example, consider these two sets S and T. Our intuition says we must have the same cardinality. In other words, the set of all positive integers and set of all negative even integers must have the same cardinality. But how can we be sure without writing down all the elements in S and all the elements in T to make sure that we have counted them all? Obviously, there are a lot of them here, but they are finite. So we need to consider another way to answer this question, even when the two sets are finite. So we'll define the cardinality of a set using a one-to-one function notation. Definition. The sets A and B have the same cardinality if and only if there's a one-to-one correspondence from A to B. When A and B have the same cardinality, we write the cardinality of A equals cardinality of B. For example, 1, 2, 3, 4, 5, 6 have the same cardinality because we can just count them and see that they both have the same elements. We can also prove this by defining a function from 1, 2, 3 to 4, 5, 6 as follows. F of 1 is 4, f of 2 is 5, f of 3 is 6. Now clearly this is a one-to-one function from this set to this set here. And therefore the cardinalities have the same. It's also an onto function if you notice, so therefore it's a bijection. Let's do a workshop now. In this case, we need to prove that the set A and the set B have the same cardinality. It is easy to count in this case since the number of elements in each set is small. But in this case, we want to prove that the cardinality A is just less than or equal to cardinality of B. What is our technique here? Suppose we can define a one-to-one function from A to B. So let's just define a function such as f of x equals 2x. If such a mapping exists, then the number of elements in A must be less than or equal to number of elements in B. As a bonus, if you can show that f is also a surjection, then the number of elements in B is less than or equal to number of elements in A. Let's take a look at proof using functions. We can show in this case that f is one-to-one. To show f is one-to-one, we assume f of x equals f of y. That implies 2x equals 2y, and it implies x equals y. And therefore f is one-to-one. But if it's not onto, given an element 8 in B, we cannot find any element in A such that f of x equals 8. Because f is one-to-one, the number of elements in A must be less than or equal to the number of elements in B. Therefore, we write the cardinality of A is less than or equal to cardinality of B. So cardinality of finite sets, you can find the cardinality of finite sets also by counting. If you take a look at the set of all positive even natural numbers strictly less than 10, and the set T is the 1, 3, 5, 7, then we know that the set of elements in S is not the same number as the set of elements in T. They're two different sets, but they have the same cardinality. to show that we can define a function from S to t such that f of n equals n minus 1. So we know f is both 1 to 1 and onto, hence s and t must have the same number of elements. So in this case, we define a function from set of positive even natural numbers strictly less than 10 to the set t, which is given by 1, 3, 5, 7. The function is f of n equals n minus 1. We can show f is both 1 to 1 and onto, and therefore, because f is a bijection, s and t must have the same number of elements. Cardinality of infinite sets are much more interesting and challenging. Since we cannot count the number of elements in infinite sets, we need to establish a one-to-one function to prove or disprove the cardinality of infinite sets. There are two types of infinite sets: sets that are infinite yet countable like natural numbers. We can count them like 1, 2, 3, 4, 5. There are also sets that are infinite and cannot be counted like n, say the set of real numbers. Countable sets, we say the set is countable if and only if it is finite or countably infinite. In this case, finite means we can count the exact number of elements. Countable infinite means we can count but can never finish counting. That is, for each n, there exists n plus 1 for all n. A key observation is that given a set S, if we can find a one-to-one function from S to n, then we can say something about the cardinality of S and n. That is, we know the number of elements in S is less or equal to the number of elements in A. That is, each element in S has a unique image in N. And N also can have more elements than S. This implies that the cardinality of S is less than or equal to cardinality of N. To show some set S is infinite yet countable, you can establish a one-to-one function from S to N and then show that S is less than N. Examples of countable sets. Here's a mapping between Z plus and the odd positive numbers. Note that each element in Z plus has a corresponding element in the set of odd positive numbers. How can we define such a function? We can see here if we define fn to be 2n minus 1, we have such a function. In other words, given n, for example, f1 maps into f1, f1 maps into 1, f2 maps into 3, and so on. So we can see that this function here, f of n, is a mapping from the set of natural numbers into the set of odd numbers. And clearly it's one-to-one function. Let's do a workshop. Let's show that set of all even positive integers is countable. Here's how we prove it. Let E be the set of all positive even integers. We can define a function f from e to n such that f of x equals x over 2. Since x is an even integer, we know that x over 2 is an integer as well, because x can be expressed as 2k for some k. Therefore, f is a mapping from e to n. To show it's one-to-one, assume f of x equals f of y. This implies x over 2 equals y over 2. This implies x is y. Therefore, the number of elements in A is less than or equal to the number of elements in N. Since N is countable, E must also be countable. Let's look at another workshop. The knowledge of surjections can be used to reason about cardinality of sets as well. Let's take a look at this example. Suppose there exists a surjection f from z plus to a, where z plus is a set of positive integers. We want to show that a is countable. Here's our proof. Since f is a surjection or function that is onto, then for any element in a, there exists some in z plus such that f of x equals y. This implies that the number of elements in A must be less than or equal to number of elements in Z plus. Since every element in A has a corresponding mapping in Z plus, and there can only be one such element in Z plus since f is a function. Hence, we can establish that the cardinality of A is less than cardinality of Z plus. And Z plus is countable, therefore A is also countable. There are some well-known sets that are countably infinite. That is, with some hard work, we can always find a one-to-one mapping from any of these sets, such as z plus z, n cross n, q plus z's cross z, and then q, into n. Or you can find a surjection from n to any of these sets. We will leave as exercises the task of finding one-to-one mappings from these sets to n. Let's do another workshop. We want to prove that the set of S is countably infinite, where S is a set of positive integers. So here's our proof. Let's define a function f from S to n such that f of x equals x minus 1 over 2. The x is an element in S, therefore it's an odd positive number. We know that if x is odd, then x minus 1 over 2 is also an integer. We first show that if f is 1 to 1, let's assume f of x equals f of y. This implies x minus 1 over 2 equals y minus 1 over 2, and it implies x equals to y. Therefore, f is 1 to 1. Since f is 1 to 1, the cardinality of s must be less than or equal to cardinality of n. Since n is countably infinite, it also implies that s is also countably infinite. The mystery of countably infinite sets. We now describe a paradox that shows there's something impossible. We'll not prove anything here, but it is an interesting way to understand the notion of countably infinite sets. With infinite sets may be possible with finite sets. The famous mathematician David Hilbert invented the notion of the Grand Hotel, which has a countably infinite number of rooms, each occupied by a guest. When a new guest arrives at a hotel with a finite number of rooms, and all rooms are occupied, this guest cannot be accommodated without evicting a current guest. However, we can always accommodate a new guest at the Grand Hotel, even when all rooms are already occupied, just by moving each guest one room away. Since there are infinitely many rooms here, there's always room for the new guest. The new guest goes into one, the one goes into two, and so on. So this shows the infiniteness, but the countable side of the set of natural numbers. Let's do another workshop. In this workshop, we'll prove that the set of all integers, including negatives, is countably infinite. So let's consider the set of all integers that are from minus infinity to plus infinity. Suppose we do a reorder of the set such as this. We write 0 and then minus 1, 1 and minus 2, 2 and so on. We can imagine that the set Z and set S are pretty much the same set, just a reordering of the elements. Let's define a function n from S such that f of n equals n over 2 if n is even, f of n equals minus n plus 1 over 2 if n is odd. Now you can see that if you write this function is 1 to 1. Let's prove it. If f of x equals f of y, both x and y must be even or both must be odd. Therefore, either x over 2 equals y over 2 or minus x plus 1 over 2 equals minus y plus 1 over 2. Both of these things implies x equals y. Therefore, f is 1 to 1 and the inverse of f from z to n, s to n also exists. This should be s here. And it's also 1 to 1. So now you can see that every element in Z, we can, if n is even, for example, let's suppose that n equals 1, n equals 1, it's odd, so you get minus 1 here. If n equals 2, you get plus 1. So minus 1 and plus 1 are obtained by 1 and 2. If n equals 0, then it's even, so therefore you get the 0. And you can continue to argue that these two sets, it's pretty much the same set if defined by this function. So next we will look at an interesting fact. Without a proof, we state that positive rational numbers are countable. It is not hard to convince that if we label all the positive rational numbers in the order shown, we can count them just as we can count natural numbers. That is, each rational number has a corresponding value in n. For example, we can label this rational number as 1, this as 2, this as 3, this is 4, 5, 6, 7, 8, 9, 10. We note that every diagonal is going in a a certain a pattern. It's 2, 1, 1, 2. And then you have 1, 2, 3, 1, 2, 3. Yeah, 1, 2, 3, 4 numerator, 1, 2, 3, 4 denominator. So if we think hard, we might be able to establish a function that is one-to-one from the natural numbers into the rational numbers, and it's on to. So one last workshop about cardinality. Suppose we have two sets with cardinality of A is cardinality of B, and cardinality B is cardinality C. We want to show that cardinality A is equal to cardinality C. By definition, we have a one-to-one function from f a to b and b to c because both cardinality of a and b are bijection. But this function is in fact a bijection because they have the same function, they have the same cardinality. So if you take the G circle F is also a one-to-one function from a to c, so we prove that cardinality of a is cardinality of c. In this case, we assume dilemma. We have to show that if f and g are bijections, so is f circle g. We'll leave this as an exercise. So this is a short video on how to think about cardinality of finite sets.